In this section, we are going to learn about concurrency. Concurrency is the ability for different parts of a program to execute independently. Parallel programming is where different parts of a program execute at the same time. So, for simplicity's sake, I will just say concurrent throughout this section. So, let's jump right into creating concurrent Rust code. Splitting the computation of a program into multiple threads might improve performance since we are taking advantage of multiple tasks at the same time. But with this comes increased complexity. We might run into issues like race conditions, where threads are accessing data or resources inconsistently, or deadlocks, which occur when two threads are waiting for each other to finish. Therefore, neither thread finishes. But we will dive into those concepts a little later on in this section, so for now, let's look at how we can create a thread. The first thing we need to do is bring it into scope, which is in standard thread. And now, to create a thread, we just use thread spawn. And then for now, we just want our thread to print out a message. And we'll say hello from a thread. Now let's run this. And we'll see that nothing was printed out, but then we run it again, and hello from a thread was printed out. And then if we run it a third time, nothing was printed out. So why is this happening? Well, it's because the main thread is actually finishing before our thread spawns and is able to print out our message. So what we can do to just make sure that we give our thread time to be created and then print out our message for us, we will use another crate called duration. And what duration is going to do for us is it's going to allow us to make our main thread sleep. So we'll say thread sleep duration from seconds, and then we'll say 1. So we just want our main thread to sleep for 1 second. So now if we run it, we see hello from a thread ran, but then you can also see that there's a little pause, and that pause is our thread sleeping for 1 second. Well, this isn't actually the best way to do this, so there is a better way of doing it, and it is by using the join method. So we can actually delete all of this, and we see that spawn returns a join handle, so we can say let handle equal and then the join handle that gets returned. And now we can say handle dot join dot unwrap. And what join is it's a form of blocking. And blocking a thread means that the thread stops running until the thread represented by the handle join terminates, join handle. So we're going to block our main thread until our thread that we until our join handle that we assigned to handle is finished executing, and that is what join is going to do for us. So now we can say we'll say print line hello from main. And now if we run this, we see that we got hello from thread and then hello from main. So this will always print out prior to this because we told our main thread to wait until this thread has completed its task. So now let's move into a little bit more in-depth threading. So let's create a vector, and we'll just call it v, and we'll assign it the values 1, 2, and 3. And then we want to spawn another thread, and for now we will move this word out of here, and now we want to print out our vector. Well, we see that we get an error. And our error says that our closure, which you can see that we have denoted here, may outlive the current function, but it borrows our vector v, which is owned by the current function. So that word that we originally got rid of, we can now put it back in, and it is called move. And move is going to allow us to force the closure to take ownership of the values it uses. So now if we try to run this, it runs flawlessly because we told our closure to take ownership of the v vector. So now let's look at how we can spawn multiple threads. So we'll keep our current vector, and then we'll create another vector that's going to handle all the threads that we spawn. So I'm going to comment this out since we want to use our v vector again. And now we can say for e element in our v vector, we want thread handles, and we want to push in spawning our vectors in. Now let's just format this to make it look a little better. Alright, so what are we doing here? So we created a new vector called thread handles. And for every element inside our v vector, so 1, 2, and 3, we are going to push in the result. So a join handle, we're going to push in a join handle into our thread handles vector. So what this is going to do, it's going to create 3 vectors for us, and they're going to be running. So while they're running, I want my main function to print main thread, I want our main thread to print out that it's the main thread. And now for handle and thread handles, we need them to join. That way we make sure that they finish executing and print out the thread that they are. So we'll run this, and we see we got main thread, thread 1, 2, 3, and now we see we have main thread, thread 2, thread 1, and thread 3. So the order that you might see may vary differently than mine, but it's a good way to show that certain threads might finish executing not in the order that they were spawned up in. So I just wanted to point that out to you. And this lecture was just a simple demonstration on how to spawn a thread, how to join the threads, and also how to use the move keyword to force a closure to take ownership of the values, because all of this will be important as we continue on learning more about threads as we continue in this section. Message passing is where threads communicate by sending each other messages containing data. For this to be accomplished, Rust uses channels, which is a concept that the standard library provides for us. The channel has 2 ends, a transmitter and a receiver. The transmitter sends data and the receiver takes in that data. A channel is considered closed when either the transmitter or the receiver end is dropped. So let's take a look at how these channels work by implementing one where the transmitter will send a string to the receiver who will then print out that string. So the first thing we need to do is import in the crate that provides channels for us, and that is standard sync MPSC. And now to create a channel, we will say let transmitter receiver, so a tuple, equal MPSC channel. Now we can spawn a thread that's going to say, and we want to pass in a value, so we'll say let val equals string from transmitting. And now we can say transmitter.send, we want to send the string, and then it returns a result, so we need to unwrap it. For our receiver to receive, we just say let message equals, let me put this semicolon before I forget, receiver dot receive, and then this also returns a result, so we need to unwrap it. And now we can print out the message that we received. And if we run this, we see transmitting. So MPSC stands for multi-producer single consumer, which is essentially a description of how channels work. So now let's look at how we can create multi-producers. But first, let's actually talk about ownership rules and message sending, because they do help us write safe concurrent code. So when we use this send function, it takes ownership of the value being passed in as a parameter, and then when receiver receives it, it takes ownership of that value. And then obviously that result is returned back here to our message. So there's nothing new with this ownership rule, but it's important to know that that is how ownership is working inside these channels. And Rust is doing this so that when we send a value, we don't try to reference or use that value later on. So an example of this is if we tried to print out our val down here. And this is going to be a compile time check for us, like all the other ownership rules. That way we cannot reference a value that no longer is valid. So it is a compile time check, which is great for us. But now let's take a look at how we can create multiple producers. So I want to make sure I don't have that error anymore. And creating multiple producers is actually pretty easy. So we can say let tx, and this is a shortened way of saying transmitter, and now we will say transmitter.clone. And now we have another producer. So I'm going to comment all of this out. That way it's a clean slate. And now we want to transmit a couple of messages. So we'll say thread spawn, and then we'll have let vec equals, and now we want a new vector to contain some strings. Transmitting, and now I'm going to copy and paste this to kind of speed it along from original. Alright, and then to transmit it, now that we have a vector, we'll say for each value in vec transmitter.send the value, and now unwrap it, because remember it returns a result. And then we want to close it out. Now let's format it to make it look pretty. And now we want to do this again, but with the second producer we created. So we'll modify that to btx, and then we will say the clone is, there we go, transmitting. Alright, so now what do we have? We have two threads spawned. Our first producer is going to transmit from original, and our second one is clone is transmitting. So now we want to set our receiver up to be able to receive all of these messages. So we'll say for rec, short for received, and receiver, we want to print out all these values that we received. And now if we run this, we see transmitting from original, and now we see clone is transmitting. So that worked exactly as we intended. We had multiple producers and one single consumer. But you might be wondering is what happens if our receiver can't keep up with the amount of messages being put in by our producers? Well, the way it works is the messages are being sent and are getting put into a queue until the receiver is ready to handle it. So the queue could become overpopulated. And when the queue is constantly being added onto and the receiver cannot keep up with it very well, we actually start to waste resources because we are using resources sending values when we actually need to allow the resources to be more allocated to processing the data being sent in. So to alleviate this, Rust does provide us with a solution called sync channel. And what sync channel is instead of just being channel, we'll say sync channel, and then in here we can put a value. So I'll put 1,000. And a sync channel is going to work the same as a regular channel, but we are specifying how many values our queue can hold. And then the send method becomes a blocking operation once the queue is filled up. So once our queue reaches 1,000 values, the next time we hit send, it's actually going to be a blocking method until our receiver starts to catch up on the amount of values that are in our queue. So this in turn allows our receiver to be able to use resources more efficiently. Remember, blocking does not necessarily mean we lose performance. We could possibly see resource improvement without losing any throughput in our channel. So this is something that I just wanted to make you aware of. Two very important traits we need to talk about are sync and send. Types that implement send are safe to pass by value to another thread, and when I say safe, I mean that they are free from data races and other undefined behavior. Types that implement send can also be moved across threads. Now, types that implement sync are safe to pass by non-mutable reference to another thread. These types can be shared across threads, so send can be moved across threads and sync can be shared across threads. Almost every Rust type is send, but there are some exceptions, such as our RC, reference counter, smart pointer. So let's take a look at that real quick. So we'll say let RC1 equals a new RC, so a new reference counter smart pointer, and we'll say string from, and then we'll just do test to keep it simple. And then we'll say let RC2 equals RC1.clone. And now we'll spawn a thread, and we'll just try to use RC2 in here. And if we run this, let me correct that error real quick. And if we run this, it says RC string cannot be sent between threads safely. Now remember, in the last section when we were talking about reference counter, I mentioned the atomic reference counter. So let's make this a atomic reference counter, which I said is safe to use across threads, and now we are able to safely use a reference counter smart pointer inside of a thread. So I just wanted to make you aware of this because these two traits are important to help ensure Rust is safe when using threads. Message passing is not the only way we can communicate. We can use mutexes. A mutex is a shortened name for mutual exclusion and only allows one thread access to some data at any given time. To allow only one thread access to the data, there is a lock. A lock is a part of the mutex data structure that keeps track of who currently has exclusive access to the data. When the thread says, "Hey, I want that data," it must ask for the mutex's lock, and then once the lock is acquired, nobody else can use that data until the lock is given back. There are two rules to follow. You must acquire the lock before using the data, and when you're done with the data that the mutex is guarding, you must give the lock back so that it is unlocked for every other thread to be able to obtain access. So now, let's see how we can use mutexes in threads. For the example, remember that arc is handy for sharing things across threads, and that a mutex is handy for mutating data that is shared across threads. So the first thing we want to do is bring the arc smart pointer and a mutex into scope. So we'll bring arc and mutex into scope. Now we're going to create a counter, and we'll make it an arc that contains a mutex, and the value is going to be 0. And now we're going to create a handles vector that's going to store all the join handles we create. So now we're going to have a little loop, and we don't care about any of the values inside, so we'll say for 0 to 10, and actually I'll make it 8, we'll say let counter equals arc clone, and then a reference to our counter variable. And now we'll say let handle equal thread spawn, and we'll say let mutable num equals counter. Now we have to lock it to gain access to the counter, and we want to unwrap the value inside. Dereference the number and add 1 to it. And that's how we're going to get our counter to go from 0 to 1, 2, 3, 4, 5, 6, 7, 8. And once we're done with that, obviously we need to push our handle into our vector for us to join our threads. So for handle and handles, handle.join, and then it expects a result. And now we can print out counter dot lock dot unwrap. That way we can see our final count. And if we run this, we see 8 is printed out. So now that we see kind of how mutexes work in a sense, let's see what would happen if we created a deadlock. So now we'll say let mutable num2 equals to counter dot lock, unwrap it. So now here we're saying, hey, we're giving the lock to num, but now we have num2 also requesting that lock. And what this is going to do is it's going to prevent this from ever being able to execute num plus 1, because we're going to get stuck here as num2 is waiting for the lock, but num holds it, but num cannot give it up because it cannot finish running its execution. So we're just never going to be able to finish running this And this is a really simple example of what a deadlock is, but it really demonstrates the purpose of a mutex in that data is inaccessible to other threads while one thread contains a lock. And so we'll close this out and then obviously get rid of that to remove our deadlock. And again, we'll just run it. And what's happening is for every thread that we create, it's getting the lock, it's adding one, it gives up the lock here, lock is given up, and now the next thread gets it, and then the lock gives up. And it does this 8 times for the 8 threads that we are creating. So that's really all there is to it, to concurrency. There are a couple of crates available to us called Crossbeam and Rayon, and I encourage you to check those out now that you have a really good understanding of how concurrency works in Rust, and you can check those crates out and see how they try to help simplify creating concurrent programs. But now that you have a great understanding of how concurrency works, let's continue on into asynchronous programming. In this lecture, I want to talk about poisoning. We learned a lot in the previous lecture about mutexes and the benefits that they give us, but you might have been wondering what would happen if the thread panicked while holding the lock. When that occurs, our mutex has become poisoned. This is obviously very undesirable because when this happens, all other threads are unable to access the data since it is likely tainted. So I went ahead and created an example here, and I instantiated a new atomic reference counted mutex, and then I also cloned it into the lock2 variable. And now remember, arc clone produces a new arc instance which points to the same allocation on the heap as the source arc, but it increments its reference count. So this arc is pointing to this one up here. So inside here, we're going to take the lock and then we're going to panic. So up here, when we acquire the lock, our lock is currently completely acceptable. But calling the panic macro here, while this thread was holding the lock, our mutex is now poisoned. And for us to recover from this, we can do a match statement. And we can try to match on what gets returned when we try to access the lock that became poisoned. And if OK is returned, then that's good. We get our value back. But if it's poisoned, then we can call into_inner to recover the mutex and the data inside of it. And when we're able to do that, then we're able to access the data as normal, and we will have our mutex back. And to demonstrate this, I can run this program, and we see that I have printed out the value 1. Well, when I created the new mutex, our value was 0. We poisoned it here, and then in our match statement, we called into_inner on it in order to recover it. And then I dereferenced the value inside of it. So here is basically 0 plus 0, 0 plus 1, and then we return 1 back. And that is what was outputted back. So it's important to have this match statement running in the event that you think one of your threads might panic while holding the lock. So it's just something for you to think about. Let's take a moment to look at a crate that we can use to help us parallelize our programs. Rayon is a lightweight data parallelizer crate that makes it super easy to convert sequential computations into parallel computations while guaranteeing safety from data races. A unique characteristic that Rayon provides is that it will automatically spawn our threads for us. But how does it know how many to spawn? Well, by default, Rayon uses the same number of threads as the number of logical CPUs available, assuming hyperthreading is enabled. Otherwise, it will just use the number of physical CPUs. So let's do a quick example of creating a program that computes the factorial of a number and compare the performance between single-threaded and multi-threaded. So the first thing we need to do in our cargo.toml file is add a couple of dependencies. And I've already added them. And so we need Rayon of version 1. And then obviously it'll take our latest version. And then also num and the latest version under 0.4. And then inside main we can start importing in these dependencies. So we'll go ahead and get them all imported in. So we'll start out with Rayon, prelude, and then asterisk to take everything in. And now we'll use num, and we want big unsigned int and 1. And then lastly we want standard, time, and instant. And this is going to be what we use to measure the time it takes for our functions to run. So we'll start off with creating our single-threaded factorial function, and it's going to accept one parameter of an unsigned 32-bit integer, and we're going to assign a big unsigned integer. And the reason we have to use a big unsigned integer is because if we used the largest unsigned integer that Rust provides us, which is a unsigned 128, our factorial would actually only be able to go up to 35. I found that out by just playing around with it a little bit. So we needed to use a big unsigned integer. That way we can use much larger values when trying to compute our factorial. So when computing a factorial, we need to do a couple of checks. We need to check if the number passed in is equal to 0 or if it equals to 1. And if it does, then we want to return a big unsigned integer 1. Otherwise, now we can actually compute our factorial. And so we'll do from 1 to num, including our number. We want to map that value, that element, into a big unsigned integer. And then we want to call the reduce method on this, and I will explain to you what reduce is in a second. I just want to get this set up, that way we can look at it. And what do we have here? No function. Oh, could this need to be capitalized? There we go. Alright, so let's break down this code. So again, we created 1 to num, which is also inclusive since we have this equal sign, and then we map it into a big unsigned integer, and then we call the reduce function on it. And the reducing function is a closure with 2 arguments. So we have argument 1 here and argument 2 here. And argument 1 is going to be the accumulator, and then x is going to be the element that we're passing in from here. So what the accumulator is going to do is we're going to say, hey, take the accumulator and then multiply it by x. And then now that's our accumulator. And then just continuously do this until we equal num. And then reduce returns an option, so we have to unwrap it in order to get the value inside of it. So let's create a test program of this, or a simple test, just to make sure that it is working correctly. And the factorial of 3 is 6. So if this runs correctly, we should see 6, which is what we have printed out. So great. So we know that it's working correctly, but just to verify, let's also do 4, and we see 24. So awesome. So everything's working properly. So now let's take this function and let's use Rayon. That way we can have the code running in parallel. So we'll just call it multi-fact for multi-threaded factorial. And our setup is going to be extremely similar. So we're going to take in an unsigned 32-bit integer, and now we're going to also return a big unsigned integer. So let's do our check again. Return 1, and then otherwise we want 1 to num inclusive. And now where Rayon comes in is we're going to call into par iter. And this is going to create an into iterator for us, but par stands for parallel. So we're going to create a parallel iterator. And now we're going to map big unit from, like we did above. And now we're going to call reduce again. And before I fill in what reduce is, let's look at the function signature up here, and we see that we have a mutable self and then f of type f. Well, if we look at this reduce function, we actually see the function signature is different. So we see that we're going to take 2 parameters in this case, so we need to modify it that way. And then this is going to allow us for parallel execution. So this reduce function actually comes inside the Rayon library. So let's set up this reduce function to allow it to be happy. So we're going to have a big unit of 1. We're going to have our accumulator. We're going to have our x value, the same as above, and then we're going to have accumulator times x. So what reduce is, and let's see if it gives us a good example here. So we have to include an identity parameter, which is what we're doing with big unit and then 1. And then the identity iterator is going to be where we start out at. So we'll have 1, and that's where our accumulator is going to start at. So it's just a different function signature provided to us by the Rayon crate to essentially do this up here. It's just typed out slightly different. And in this case, it's just going to return our item to us, so we do not have to unwrap this. So now let's look at this and make sure that our factorials are computing the same value. So we see 24 in both, and then just to make sure, let's do 3 again and make sure each one prints out 6. So great. So both of our factorial functions are printing out the correct values as we expect. So now let's create a benchmark for this. And this is where our time instant comes into play. So now we're going to create an instant and assign it now. And now we're going to calculate our factorial of 50,000. And now we want to print out how much time it takes for that computation. So we'll give it a little bit of styling. So we want it to print out 2 decimals into the second as seconds, or just 2 decimals. And we'll say now dot elapsed to get the time differentiation. So from time now to time now here as well. And then the difference between the two, so the time elapsed. And now we want to do this again, but we want to do it with our multi-factorial. And so, if we run this now, the factorial of 50,000 single-threaded is going to take 4.92 seconds, and our parallelized factorial actually took 169.5 milliseconds. So that just shows you how much faster it is to run programs in a parallel manner. So if we run it again, and this time 40,000, we see that we're seeing magnitudes higher of performance speedups, which is why I wanted to show you just how awesome this Rayon crate is. So hopefully this was a very insightful lecture for you into the power that parallelizing our applications can provide for us. I hope you enjoyed this section on concurrency. We will now be going over the solution to the assignment for this section. The question was, using Rayon for this solution, research Rayon join. Once you have read into Rayon join, in the Fibonacci join function of the provided source code, create a solution that utilizes Rayon join so that we can see a performance enhancement in our Fibonacci solution. So, once you research Rayon join, you took away some information where Rayon join takes two closures and then possibly runs them in parallel. In this case, they will be ran in parallel. And then join is going to return a pair of the results from those closures. So we know that we're going to get some values back from the two closures. So we'll create a tuple that is going to store values A and B, and we're going to call Rayon join. And we know that Rayon join wants two closures, so we'll give it this closure where we're going to call the Fibonacci recursive function, and in here we're going to pass in n-1. And now we know that we need to pass in another closure, and this time we will pass in n-2. And then simply all we have to do is add A plus B. So now we can run this, and we see that in our first iteration of fib recursive, which is the non-parallelized function, we see that Fibonacci recursive actually takes a decent bit of time to actually execute, because what it's doing is it's creating our series of numbers for us, and it happens to be pretty intensive computation. So we see we get a really large number here, and it took us 18.5 seconds. But when we ran it with Rayon's join, therefore introducing some parallelism, we were able to knock off a little over 6 seconds and still generate the correct solution. So hopefully this is an eye-opening assignment on how much time can be saved when you introduce some parallelism into your solutions. So I hope this assignment was fun for you, and I will see you in the next section.